Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're going to be covering chapter 3 for general chemistry, and this chapter is all about stoichiometry. Now, before we go over the objectives that we're going to cover in this lecture, I want to make note of a really cool resource I found recently. This resource is called Slay School, and they're really cool because you can take the URL of a YouTube video that you're interested in, a YouTube lecture video, and upload it on this website. And what it will do is generate a flashcard deck based off of that video that you can study. And that's really cool for any kind of lecture video you're interested in. Just, plug it in and let the website generate a flashcard deck for you to study. Give it a try. They have a free option. They also have a premium paid option. Whichever you like and feel like is right up your alley, I highly recommend. Now, with that out of the way, let's talk about the objectives that we're going to cover in this chapter. The first three objectives are about atomic mass, mole, and molar mass. These first three objectives are topics we did cover in chapter 2, but they're going to be worth going over and kind of building on before we cover any other concept in this chapter. If you feel super confident on these topics and you really don't want a refresher, you can skip about the first 15 to 20 minutes. I won't be offended, I promise. After that, we're going to jump into objective 4, titled Percent Composition of Compounds. There are two ways of describing the composition of a compound in terms of the number of its constituent atoms and in terms of the percentages by mass of its element. And we're going to discuss both here. After that, we're going to move into objective 5, titled Determining the Formula of a Compound. This is going to involve us discussing empirical formulas. An empirical formula for a compound contains the smallest whole number mole-to-mole ratio of elements in that compound. Then the next two objectives are about chemical equations and balancing chemical equations. This is really important, and this is one of my favorite topics to teach in this chapter, so I'm really excited about that. Then we're going to move into a discussion on stoichiometric coefficients. So up until this objective, we would have covered that mole is a number word, like dozen is a number word, and we would have covered that mole relates to mass. Then when we make it into this objective, we're going to learn that the mole concept provides mole-to-mole ratios, and that's going to be really important for a lot of different calculations we're going to learn how to do. Then last, but certainly not least, we're going to cover limiting and excess reagents. So with that introduction, let's go ahead and get the lecture started, and let's review a few topics from chapter 2. That's going to be atomic mass, mole, and molar mass. Now, the concept of mass, atomic mass, and moles are intricately connected, and they're really fundamental to understanding chemical reactions and the composition of substances. We're going to start with atomic mass unit. The atomic mass unit is a standard unit of mass that quantifies the mass of atoms or molecules. It's defined as 1/12 of the mass of a carbon-12 atom. Let me repeat that. It's defined as 1/12 the mass of a carbon-12 atom, which is an isotope of carbon with 6 protons and 6 neutrons. The carbon-12 isotope is stable, and its abundance makes it a standard for measuring atomic masses. One atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms. The atomic mass of an element, usually found on the periodic table, is expressed in AMU, and it represents the average mass of all the isotopes of that element, taking into account their relative abundances. We discussed this in great detail in chapter 2. The next topic is moles. A mole is a unit that measures the amount of substance. Like the measure 1 dozen signals that you have 12 of some object, 1 mole of any substance contains exactly 6.022 times 10 to the 23 entities. This could be atoms, particles, molecules, ions, etc. This number is known as Avogadro's number. The mole allows chemists to count particles by weighing them. The mass of 1 mole of a substance is equal to its molecular or atomic mass in grams. And that helps us segue into the last word we want to cover, molar mass. Molar mass is the mass of 1 mole of a substance, element, or compound, and it's expressed in grams per mole. Now, a chemical compound is ultimately a collection of atoms. For example, methane, which is the major component of natural gas, it consists of molecules that each contain 1 carbon and 4 hydrogen atoms. Methane is CH4. Now, how can we calculate the mass of 1 mole of methane? That is, what is the mass of 6.022 times 10 to the 23 methane molecules? Now, since each methane molecule, each CH4 molecule contains 1 carbon and 4 hydrogen atoms, 1 mole of CH4 molecules would contain 1 mole of carbon atoms and 4 moles of hydrogen atoms. The mass of 1 mole of methane can then be found by just summing the masses of the 1 carbon, which weighs 12 grams, and the mass of 4 hydrogens. Each hydrogen is 1 gram, and 4 would be a total of 4 grams, summing that up to get 16 grams. This is the mass of CH4. Now, we can put all of these topics together. Sorry, my voice kind of cracked at the now there, didn't it? Now that we've defined these 3 terms, how do we connect them all together? And by that, I mean, how do we convert from one form into another? So that's what we want to talk about next, how we kind of convert between number of atoms or particles to moles to mass and any variation of that. But before I go over this flow chart, I want to make a quick note on 2 words that are really important. Dimensional analysis, you heard this in chapter 1, and now this chapter is all about stoichiometry. So I want to kind of define these 2 terms. Dimensional analysis is a mathematical method that's often used in calculations to convert values from one unit to another. And it does this because it involves the use of conversion factors, which are ratios of equivalent measurements. Now, stoichiometry, this is a branch of chemistry that deals with the quantitative relationship that exists among the reactants and products in chemical reactions. These relationships are often determined through balanced chemical equations. And while stoichiometry often uses dimensional analysis as part of its calculations, it also involves understanding the relationships between different substances in a chemical reaction. Now, going over how to convert between number of particles to moles and moles to mass and any combination of that, we're going to be introduced to a couple of conversion factors that are going to be really important for stoichiometric problems that we're going to cover in this chapter and probably in a lot of other chapters as we go through our general chemistry course. So let's get started. If you know the number of particles or atoms and you want to convert to moles, how do you do that? Well, if you know the number of particles or atoms, you can convert that to moles by dividing by Avogadro's number. Now, I want to also show you what that looks like when you're setting up a problem. So if you know the number of atoms of carbon and you want to convert that to moles of carbon, we said we're going to divide by Avogadro's number. So if we know we have 10 atoms of carbon and we want to convert that to moles of carbon, we're going to divide by Avogadro's number. Now, the relationship is that 1 mole of some element is equal to 6.022 times 10 to the 23 atoms of that atom or whatever. All right. So now if we have number of atoms for carbon, 10 atoms of carbon, and we want moles of carbon, dividing by Avogadro's number means that we put 6.022 times 10 to the 23 atoms of carbon in the denominator, hence dividing by Avogadro's number for 1 mole of carbon. And you notice that the units atoms of carbon cancel out, and the answer we get from this calculation is going to have units of moles of carbon. So that's what we mean when we say to go from number of atoms or particles to moles, we're going to divide by Avogadro's number. It's really important to see what this looks like in a setup, right? Because some of the problems we're going to do down the line are going to involve multiple steps and multiple conversions. So it's good to know how to order these kinds of conversions in a way that cancels out unwanted units and gets us an answer in our desired units. Now, what about if we're going the other way around? All right, what if we know the number of moles and we want to get the number of particles, for example? Well, in this case, we're going to have to multiply by Avogadro's number. So let's say we know we have 3 moles of oxygen and we want to know the number of oxygen atoms. What that means is we're going to multiply by Avogadro's number. So now we put Avogadro's number in the numerator, 6.022 times 1023 atoms of oxygen per 1 mole of oxygen. Notice how the units cancel out here. And we're going to get our answer in units of atoms of oxygen, which is exactly what we want. So again, going from number of particles to moles, we divide by Avogadro's number. Going from moles to number of particles, we multiply by Avogadro's number. Okay, so far so good. What about if we have number of moles and we want to get mass? What do we do here? We're going to have to multiply by molar mass. So if we know we have 7 moles of hydrogen, and we want to get grams of hydrogen, the mass of hydrogen, we're going to have to multiply by molar mass. You can get this from the periodic table. The molar mass for hydrogen is 1.008 grams per 1 mole. So we're going to put 1 mole of hydrogen, all right? And this is supposed to be a H, but it kind of looks like a number sign. 1 mole of hydrogen is 1.008 grams of hydrogen. Notice how moles of hydrogen cancels out. And we're left with units of grams of hydrogen. So that's the units that would be associated with our answer. Now, if we're going the opposite way, if we know mass and we want to get moles, here we're going to divide by molar mass. And so this kind of helps us introduce 2 really important conversions, right? For stoichiometry, we have Avogadro's number, 1 mole equals 6.022 times 10 to the 23 atoms. And the other one is molar mass. 1 mole of some element equals its mass. And we use these 2 kinds of conversions to move between number of particles and atoms to moles to mass and any variety of that. And with that, I also want to cover, well, if you know number of particles and you want to get to, let me do some erasing here. If you know the number of particles and you want to get mass, what do we do to do that? Well, you'll just follow the arrows. Number of particles to get to mass, you're going to first divide by Avogadro's number, and that gets you to moles, and then you'll multiply by molar mass to get to mass. And the same way goes if you're working the other way around. You want to follow the arrows. If you're going from mass to number of particles first, you'll divide by molar mass, that gets you to moles, and then you multiply by Avogadro's number to get number of particles, atoms, or ions. Wonderful. So now that we've covered this, let's do some example problems to make sure we really understand how to convert. This first problem says a silicon chip used in an integrated circuit of a microcomputer has a mass of 5.68 milligrams. How many silicon atoms are present in the chip? Okay, that's wonderful. What do we know? We know we have 5.68 milligrams. So what we know is mass. And what we want to get is number of atoms for silicon. Okay, well, if we look at our flow chart, we can get a kind of feel of the steps that we're going to need to do that conversion. We're going from mass all the way to number of atoms. The steps for that are to divide by molar mass and then multiply by Avogadro's number. Let's go ahead and write that down for ourselves so we don't forget. First step, we divide by molar mass. Second step, we multiply by Avogadro's number. Now, before we get started though, there is one caveat here that we have to be aware of. Molar mass is in units of grams per mole, but we're given mass in milligrams. So actually the first step that we need to do, we'll call it step 0, is convert milligrams into grams. Okay, so let's go ahead and get this started. Let's do step 0. We have 5.68 milligrams. We want to convert that to grams. We know this conversion factor. We talked about it in lecture 1. Okay, 1,000 milligrams in 1 gram. And so we can carry this out to get the gram of silicon atoms. This is going to give us 5.68 times 10 to the minus 3 grams of silicon. Beautiful. So that's the first step. Okay, now the next step is to take that mass in grams and convert it to moles by using molar mass. All right, and specifically by dividing by molar mass. Now we can look at the periodic table to get the molar mass for silicon. It's 28.9 grams per mole. Now we're going to put the 28.09 grams of silicon in the denominator for 1 mole of silicon in the numerator. And this way, the units grams of silicon cancel out, and we're going to get our answer in units of moles. And so if we plug this into a calculator, we're going to get 2.02 times 10 to the minus 4 moles of silicon. Wonderful. That's step 2 completed. Now we can go ahead and move into our last and final step. We can take the number of moles that we have and convert it to number of atoms by multiplying by Avogadro's number. And we know this Avogadro's number, the conversion is 6.022 times 10 to the 23 atoms of silicon are in 1 mole of silicon. And notice how moles of silicon is in the denominator so that we can cancel out this unit. And our final answer is going to have units of atoms of silicon. So if we plug this into a calculator, we're going to get 1.22 times 10 to the 20th power atoms of silicon. And there we have it, our final answer. Cool. So this problem, we calculated the number of atoms. Let's do another example problem. This one says, cobalt is a metal that is added to steel to improve its resistance to corrosion. Calculate both the number of moles in a sample of cobalt containing 5 times 10 to the 20 atoms and the mass of the sample. Okay, so what we know is that we have 5 times 10 to the 20 atoms of cobalt. We want to figure out moles of cobalt and mass of cobalt. So let's go back to our flowchart and just make sure we remember how to do a conversion like this. We're starting off with number of particles or atoms, okay? And we want to get moles and mass. Now, the first step we could do is get moles by dividing by Avogadro's number, and then we can go from moles to mass by multiplying by molar mass. So those are our steps to get both moles of cobalt and mass of cobalt. So let's go ahead and get started. We can write 5 times 10 to the 20 atoms of cobalt. We're going to multiply this we're going to divide this by Avogadro's number. So we're going to put 6.022 times 10 to the 23 atoms of cobalt is equal to 1 mole of cobalt. And notice how atoms of cobalt cancels out. We're going to get our answer in units of moles of cobalt. If you plug this into a calculator, you're going to get 8.30 times 10 to the minus 4 moles of cobalt. Okay, so we did our first requirement. We completed our first requirement. We figured out moles of cobalt. Now let's figure out the mass of cobalt. We know we have 8.3 times 10 to the minus 4 moles of cobalt, and we want to get mass. We can do this by multiplying by molar mass. All right, we can get the molar mass of cobalt from the periodic table. For 1 mole of cobalt, we have 58.93 grams of cobalt. Moles of cobalt cancels out, and our answer here is going to be 4.89 times 10 to the minus 2 grams of cobalt. So we figured out the moles of cobalt, and we figured out the mass of cobalt. And therefore, we've completed 2 practice problems on how to convert between different units. We did calculating numbers of atoms, and then we calculated the numbers of moles and mass for this second example. Cool. Now what we can do is move into objective 4. Objective 4 is titled Percent Composition of Compounds. Now there are 2 common ways of describing the composition of a compound. 1 in terms of the number of its constituent atoms, and 2 in terms of the percentages by mass of its elements. We can obtain the mass percents of the elements from the formula of the compound by comparing the mass of each element present in 1 mole of the compound to the total mass of 1 mole of the compound. So the best way to understand this is through an example. So let's take ethanol, which has the molecular formula C2H5OH. We can figure out the mass of carbon by taking how many moles of carbon are present in ethanol and multiplying it by the molar mass. So there are 2 moles of carbon in ethanol, and we can multiply that by the molar mass of carbon, which is 12.01 grams per 1 mole, and we get the mass of carbon to be 24.02 grams. We can do the same for hydrogen. There are 6 moles of hydrogen, and we can multiply it by the molar mass of hydrogen to get 6.048 grams. And then last but not least, we can do the mass of oxygen. There is 1 mole of oxygen. We can multiply it by its molar mass to get 16 grams of oxygen. With that, we can figure out the mass of 1 mole of ethanol by summing up these quantities, 24.02 plus 6.048 plus 16 grams, and that gives us 46.07 grams for the mass of 1 mole of ethanol. Then we can start to figure out the mass percent, often called the weight percent, of each atom as well. So if we were trying to figure out the mass percent of carbon in ethanol, we can compute this by comparing the mass of carbon in 1 mole of ethanol to the total mass of 1 mole of ethanol. We have both of those quantities. We figured out that the mass of carbon was 24.02 grams. And we figured out that the mass of 1 mole of ethanol was 46.07 grams. So we divide 24 by 46 and then multiply that by 100% to get the mass percent of carbon to be 52.14%. And then we can do the same thing for hydrogen. We get 13.13%, and we can do it the mass percent of oxygen as well, and we'll get 34.73%. Now, our next objective 5, is called determining the formula of a compound. Here we want to talk about the empirical formula. The empirical formula of a compound, it contains the smallest whole number mole-to-mole ratio of an element in that compound. This is often different from the molecular formula, which shows the actual number of atoms of each element in a molecule. If the empirical formula and molar mass of a particular compound are known, then the molecular formula, it can be easily determined. So let's do an example. Let's say that we have an unknown compound that has an empirical formula of CH2O and a molar mass of 120 grams. We want to figure out what the molecular formula for this unknown compound is. How do we go about this? Well, the first step is to figure out the molar mass of this empirical formula, CH2O. Carbon is 12 grams, oxygen is 16 grams, hydrogen is 1 gram, and there's 2 of them for a total of 2 grams. And if we sum these up, we'll get 30 grams per mole for CH2O. Now, a molecular formula will always be a whole number multiple of the number of atoms present in the empirical formula. And so dividing the molar mass of a compound by the molar mass of the empirical formula will give the multiple needed for determining the molecular formula. So in this case, the molar mass of the unknown we were given to be 120 grams per mole, and the molar mass of the empirical formula we calculated to be 30 grams per mole. And if we divide 120 by 30, we get 4. This is the number we want to multiply CH2O by. That 4 gets distributed to the carbon, hydrogen, and oxygen, and we get C4H8O4. This is the molecular formula for our unknown compound. Wonderful. So now let's put together objective 4 and objective 5 and do this example problem. This example problem says, what is the empirical formula of a compound consisting of 48.64% of carbon, 8.16% of hydrogen, and 43.2% oxygen by mass? Now, when we're attempting this problem, we have to keep 2 ideas in mind. 1, percent composition is percent by mass, and 2, an empirical formula is the smallest whole number mole-to-mole ratio. Okay, now when the percent composition by mass is given, it's often easiest to assume that we just have 100 grams of this unknown. And that's easy to, this is recommended to do because now calculating the mass of each atom, carbon, hydrogen, and oxygen, is going to be a lot easier. So for example, we know that we have 48.64% of carbon. If we have a total of 100 grams of unknown, this means that we have 48.64 grams of carbon. And the same goes for hydrogen, 8.16% hydrogen. We have 8.16 grams of hydrogen. And same for oxygen, 43.2% oxygen means we have 43.2 grams of oxygen. Now that we have our masses for carbon, hydrogen, and oxygen, we can determine the number of moles of each element in this 100 grams of unknown. And we can do that by dividing by molar mass. So for carbon, we can multiply this by 1 mole of carbon equal to 12.01 grams of carbon. Grams of carbon cancels out and we get our answer in units of mole of carbon. It's going to give 4.05 moles of carbon. And then we'll do the same thing with hydrogen. 1 mole of hydrogen is equal to 1.008 grams of hydrogen. And that cancels out the grams per hydrogen and we get our answer in moles of hydrogen, 8.10 moles of hydrogen. And then last but not least, we want to do this with oxygen. 1 mole of oxygen is 16 grams. Grams of oxygen cancels out and we get 2.7 moles of oxygen. Now again, an empirical formula is the smallest whole number mole to mole ratio. And to get that ratio, we're going to need to divide the number of moles of each element by the smallest number of moles. Well, we have 4.05, 8.1, and 2.7, which is the smallest? 2.7. So we're going to divide each of these numbers by 2.7. So for carbon, 4.05 divided by 2.7 is going to give us about 1.5. For hydrogen, we're going to get 3. And for oxygen, we're going to get 1. And so the mole to mole ratio is 1.5 to 3 to 1, or in other words, C1.5H3O1. But we want to express an empirical formula as the smallest whole number mole to mole ratio. And so in order to express this using whole number subscripts, we have to multiply this by a number to get this 1.5 to a whole number. And the easiest way to do that with the smallest number possible is just multiplying this by 2. And so what we get is C3H6O2. That is our empirical formula. All right, with that, we've completed objective 5. We can move into objective 6, but actually we're going to end the lecture video here, and in the next video, we'll pick right back up. Again, I want to reiterate, if you want to make a flashcard deck to study this lecture or any lecture, highly recommend using Slay School. If you have any questions, comments, concerns, leave them down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.